Hey, welcome to Chemistry with Mrs. Mays. Today we're working on an honors chemistry topic called Advanced Molecular Structures. In class we did some basic structures, but now we're going to look at compounds with an incomplete octet, expanded octet, multiple bonds, polyatomic ions, or even a resonant structure. So let's start with basic formula drawing. The first thing that we'll need to do is find the total number of electrons, valence electrons in the polyatomic ion or in the molecule. So for phosphorus, I have 5 valence electrons. Chlorine has 7, but there are 3 of those. So the total number of electrons for the entire thing, if I add them all together, is equal to 26 electrons. So far, so good. Now we'll write the symbol of the least electronegative element as our central atom. It's usually the first one in your formula. In this case, it would be phosphorus. Our next step is to connect other atoms to the central atom with a single bond, or a dash. So I put my 3 chlorines around the phosphorus. Doesn't matter if you do up or down or whatever, just on 3 different sides, not all clustered together on the same side. Okay, so next we count each of the single bonds as a pair of electrons, and we'll see how many do we already have. So I've got right now 2, 4, 6 electrons total, but I need 26 altogether. So I've got to add more electrons. We'll start by putting them around the peripheral atoms, the outside atoms. So chlorine gets to have 8, and then this chlorine needs to have 8. And this chlorine needs to have 8. Now let's count our electrons again and see where we're at. We had 6 before, so here's 2, 4, 6, 8, 10, 12, 14, 16, 18 new electrons, and we are up to 24. I need to have 26. So for my last electrons, I'm going to put them on the central atom so that that one has 8 electrons too. Now phosphorus gets to have 8, and so does chlorine. Now we're going to check our formula and make sure that, first of all, every atom needs to have a full outer shell. And then secondly, did we use up all of the electrons? And we just counted them. We have 26 electrons. We didn't use too many, and we didn't use too few. So everything checks out great. Now, what if we're doing more complicated structures? We'll always follow these guidelines. First of all, hydrogen atoms only form 1 bond. Fluorine atoms also form just 1 bond. And other halogens usually form 1 bond unless the halogen that we're talking about is the central atom and it's bonded to smaller atoms, or sometimes when they're bonded to oxygen, they'll do some crazy things. Oxygen atoms normally form 2 bonds. Nitrogen atoms will normally form 3 bonds, and carbon atoms normally form 4 bonds. And if you look at their Lewis structures, you'll see why that is true. Look at oxygen has 2 places where we could form a bond with these electrons that don't have a partner yet. Nitrogen has 5 valence electrons, so we've got 3 places to make attachments here, here, and here. And then of course carbon has 4 valence electrons. That gives us 4 places to form a bond. Okay, let's try it. We'll draw the structure for nitrogen trichloride. So nitrogen trichloride is NCl3. Nitrogen has 5 valence electrons, chlorine has 7, and there are 3 chlorines to consider, so 21 plus 5 is 26 electrons to find a place for. Let's put nitrogen in the center because it is the only one there. The nitrogen is the thing that we have only 1 of, so we'll put that in the middle, and then the chlorines will hang off the ends. So I have 6 electrons now. Let's give chlorine more electrons. So we'll fill in octets for all of the chlorines because they're not going to form double bonds, so it makes sense just to give them their octet. And that brings us up to 24 electrons used, right? So 6 here, 2, 4, 6, 8, 10, 12, 14, 16, 18, and 18 plus 6 is 22. 24. Yeah, I can count. So my other 2 electrons, my remaining 2 electrons go above the nitrogen. It looks a lot like PCl3 that we just did. And that makes sense because nitrogen and phosphorus are in the same family. So now let's move on to something a little more complicated. The octet rule in a Lewis structure is never going to be violated by peripheral atoms. That means the ones on the outside. Central atoms may sometimes violate the octet rule. Sometimes, if we have something really small, like beryllium, boron, and aluminum, then we won't have room for 8 electrons around it. Beryllium has only 4 protons, so they'll sometimes have an incomplete octet because they're so small. Then elements belonging to the 3rd period or higher, that means like higher numbers, like n equals 4, 5, 6, and so on, they may have an expanded octet because those elements have access to empty d orbitals. And because it's in the d orbitals where we're expanding the octet, then that means atoms that belong to the 1st or 2nd period, they will not ever have an expanded octet because there is no such thing as a 1d orbital or a 2d orbital. No expanded octets then for the first 2 rows. So let's try out some of these. If I start with boron and I put my 3 electrons around my boron, there's my valence electrons, then where do the 3 chlorines go for boron trichloride? Well, it seems like they should go where my lonely electrons are. These guys need a partner, so let's put our chlorines there. So chlorine gets to have 7 electrons. We'll partner up here. Seven electrons for this chlorine. So now we can see where the partners exist to form the bond, the covalent bonds between boron and chlorine. So let me translate that into a line. So we changed those to single bonds, and now let's count the electrons. Boron has 5, nope, that's a lie. Boron has 3 valence electrons, and each chlorine has 7. So 21 plus 3 gives us 24 total electrons. Let's count them up. 2, 4, 6 in the bonds. 8, 10, 12, 14, 16, 18, 20, 22, 24. So now we're done. We don't have any more electrons, and boron only has 6 electrons around it. But that's okay, because boron is small, and it can accommodate an incomplete octet better than other atoms could. So it's stable this way. Now let's try sulfur hexafluoride. Sulfur hexafluoride is SF6. So we have to count 6 electrons for sulfur's valence electrons, and then 7 for each of my fluorines, multiplied by 6, because there are 6 of them, and that gives us 48 electrons that we have to figure out where to put them. We'll start with our central atom. Sulfur is less electronegative than fluorine, so it goes in the middle. Then we'll put 6 fluorines around the edge. Okay, so that's 12 electrons so far. Now let's get the rest of the electrons for the fluorine. We'll pair them up. Fluorine needs to have an octet. So there's 6 more. We're up to 18. And then there's 6 more. So now we're at 24. 6 more gives us 30. And another 6 around this fluorine, so we're up to 36. And now we have 42. And one more set of 6 will give us 48. So there's the structure of sulfur hexafluoride. And now sulfur has 12 valence electrons around it. That's way more than the octet rule says it should have. But sulfur is in energy level 3. So it will have access to 3d orbitals that haven't yet been filled in by the transition metals. So it's going to put some of these electrons in 3d orbitals so that it can form a bond with the very electronegative atom of fluorine. Now let's look at an instance where we have multiple bonds. Sometimes more than one pair of electrons may be shared between two atoms. Multiple bonds are going to be stronger than single bonds because now we're involving more than one pair of electrons. They're also going to be shorter than single bonds because that attraction is greater. And since the distance between the positive nucleus and the negative electrons is smaller, then it's going to take more energy to separate the particles that are joined together by multiple bonds. So multiple bonds store more energy than single bonds. That's why nitrogen, that tends to form 3 bonds, is going to have a lot of energy in it, and it makes a lot of the explosives that we use, like TNT is trinitrotoluene, because there's triple bonds in that compound. So let's draw the structure for carbon dioxide so we can see how to do the multiple bonds. I'll start with the carbon in the center and put its normal 4 electrons around it so that you can see why we would need to use double bonds in carbon dioxide. So oxygen gets to have 6 electrons, and I have 2 oxygens. They each get 6 valence electrons. And then we're going to look for a partner for every electron here. So I can see right here, these can partner up, right? That's easy to spot. But now I need a partner for this guy. So let's join up with this electron for carbon, and then here we're going to have to sort of move things around, right? So let me adjust our picture to show the double bonds now. So when those electrons shift around a little bit, I get a double bond on either side of the carbon, and the electrons that did not get to be in a bond, they just stay as dots right where they were. Or you could spread them out a little bit to minimize repulsion. So sometimes you'll see carbon dioxide drawn like this to spread the bonded electrons out and keep them away from non-bonding electrons. So sometimes we see carbon dioxide drawn that way. If you have to use double bonds or triple bonds even to fulfill the octet, make sure that your peripheral atoms get the octet first before you worry about the central atom. Polyatomic ions contain non-metal atoms that are covalently bonded to each other in addition to gaining or losing electrons so that they could make a charged particle, because that's what ions are, charged particles. So if you have a cation or a positively charged ion, then the number of electrons that have been removed from your neutral species is equal to the charge on that cation. On the other hand, if you have an anion, which is a negative ion, then the negative charge on that anion represents the number of electrons that have been added to it. So when we're doing the math to count up the total number of electrons, we'll have to consider what the charge is telling us to do. So we'll follow the same steps as before, only this time we'll add or subtract electrons according to the charge of the ion. Then we'll sketch the structure like we did in the basic molecular structure sketching, and enclose the Lewis structure in the square brackets so that we can show that the charge of the ion belongs to the entire group of atoms. Let's try this out. Start with ammonium, which is NH4+. Let's count up our electrons first. Nitrogen has 5 valence electrons. Hydrogen has 1, and there are 4 of them. But since I have a positive 1 charge, that means that a cation has removed an electron, so I'm going to take 1 away. So I had 9, and I take 1 away, so now there's only 8 electrons left. So I'm going to put my nitrogen in the middle of the 4 hydrogens. Remember, every single bond represents a pair of electrons. So as soon as I have surrounded my nitrogen with my 4 electrons, or with my 4 hydrogens, that means I have 8 electrons in my structure already. So I'm done, except for now, we got to put the charge. Put the square brackets around the whole thing, and then put the charge like you normally would put a charge as a superscript. We're still going to do that on the outside of the brackets to show that the +1 charge belongs to this entire group of atoms known as ammonium. Sometimes there's more than one correct Lewis structure that can be drawn. Even though they're different structures, the structures would be equally correct, and so they're considered to be resonant structures. That means they coexist and sort of merge together, but they all exist at the same time, so that's why we call them resonant. And since the electrons don't belong to one particular bond, they're referred to as delocalized electrons because they're sort of spread out equally between the entire structure. So if we were trying to sketch the carbonate ion, we would have to use resonant structures. Let's count the electrons first. Carbon has 4 valence electrons. Oxygen has 6 valence electrons, and there are 3 oxygens here. Plus, I have 2 extra electrons for my -2 charge. So altogether, what's that make? 18 and 4 and 2 more is 26 electrons total. So we'll start by putting the carbon and the 3 oxygens around it. And now our next step is to give all of the oxygens 8 electrons. And I'm going to start here by putting 8 electrons around my carbon at the same time. So I made a double bond. Now my oxygen has 4 electrons here, so I need 4 more to give that one 8 electrons. And the single bonded oxygen needs 6 more electrons around it. So let's put those electrons for each of the remaining oxygens. And then we'll count up our electrons and see how we're doing. So I need 26 total. In my bonds, I have 8 electrons. Then there's 10, 12, 14, 16, 18, 20, 22, 24. So I need 2 more electrons. Okay, I only came up with 24 electrons because I did my math wrong. So fix that. 24 electrons are all that we need. And then we put brackets around it and -2 charge. So there's the carbonate ion. That's a valid structure, but it would be just as valid to draw it this way with the double bond on the other side. So if I had my double bond on this other oxygen instead, it would be just as good of a structure as the first one that we drew. So that's also a valid structure for the carbonate ion. As long as we put the brackets around it, then that one's just as good. But who's to say that we couldn't put the double bonded oxygen at the bottom instead of the ones on the sides? That's also a valid structure. So all of these are correct. Which one is going to be true? The fact is, they're all true all at the same time, except we won't really have a double or single bond. We'll have something more like a 2/3 bond or so, or 1.5 bond. So this double bond gets sort of spread out among all of them, and none of them have a true double bond or a true single bond. They sort of share. So we use dashed lines to show that the double bond can be in all of those places. Another way to show it is to draw arrows like this to show that you have a resonant structure between the 3 different Lewis diagrams. It could be any of those 3 pictures. The truth is, the electrons are everywhere all at the same time. So now that you've had a chance to work with more complicated structures, you can practice the ones in the packet that is the supplement for honors chemistry. So tackle the practice problems and bring them to your teacher if you get stuck on any of them.